Welcome back, everyone, to this discussion on feature scaling. Feature scaling provides many benefits to our machine learning process. Some machine learning models that rely on distance metrics, such as k-nearest neighbors, actually require scaling in order to perform well. Let's discuss the main ideas and benefits behind feature scaling. The most important benefit is that feature scaling improves the convergence of the steepest descent algorithms. And what we mean by that are algorithms like gradient descent in trying to minimize the loss function. Those gradient descent algorithms do not possess the property of scale invariance. So what we mean by that is that if you have features that are on different scales and you're trying to use something like gradient descent to figure out the optimal coefficients, certain weights for those coefficients may update faster than others, since the feature values, xj, play a role in those coefficient or weight updates. Essentially what we mean is, if you can imagine gradient descent in multiple dimensions, and you have some features on much different or much larger scales than others, then the weights that are being restricted to those really large scales are going to take longer to update than the scales for features that are much smaller. And so what you want is that all the features are on roughly the same scale. That way, the gradient descent, as far as the convergence of the optimal coefficients or weights, can take around the same amount of time for each of those features. So that really is the critical benefit of feature scaling. It's related to gradient descent and helping that algorithm perform optimally. Now, there are some machine learning algorithms where scaling is not going to have any effect. And those can be things like regression trees or decision trees or things like random forest. Essentially, decision tree based algorithms where you're not really performing any sort of gradient descent to solve for. Scaling the features so that their respective ranges are uniform is also important when we're comparing measurements that have different units. What happens is scaling the features allows us to directly compare model coefficients on one feature to each other. So there are a few caveats to feature scaling. One caveat is that if you just train the model to feature data that was scaled, that means for new incoming unseen data, you will also have to scale it before feeding it to the model. It also affects direct interpretability of feature coefficients. While if you scale all the features to the same range, that does make it easier to compare one coefficient to another, it is harder to relate that original feature to that new coefficient since you had to scale it first, which means you are no longer dealing with one unit of the original feature, but instead one unit of the scaled feature. So it's a bit of a trade-off between being able to compare coefficients between each other versus being able to compare coefficients to your original unscaled feature. Now, feature scaling, the main benefits are it can lead to great increases in performance. And what we mean by that are performance metrics. Many machine learning algorithms have a boost in machine learning performance when you actually perform feature scaling. The other benefit is that in some cases, it's absolutely necessary just for the model to get any sort of good results. And we're talking about things like k-nearest neighbors in that aspect. And there's pretty much virtually no real downside to scaling features. So if you're ever unsure whether or not you should be scaling features for a particular machine learning algorithm, you can go ahead and just scale them anyways, since it really doesn't take too long to compute the scaling, and it's not going to harm any other algorithms. Now, there's two main ways to scale features, and they're called standardization and normalization. Standardization rescales data to have a mean, that is mu, of 0 and a standard deviation of 1, which means you're essentially standardizing all your data to follow a standard normal distribution. So you could have negative values there. Normalization, on the other hand, rescales all data values to be between 0 and 1. So standardization is simply rescaling the data to a standard normal distribution, that is having a mean of 0 and a standard deviation of 1 unit. This is pretty simple math to go through. You essentially calculate a mean, calculate a standard deviation, and then for every single data point, you're going to subtract that mean and then divide by the standard deviation to get your updated or scaled feature. Keep in mind that the namesake can be a little confusing. Sometimes people actually say normalization when it's really standardization, and that's because standardization, technically speaking, can be referred to as z-score normalization. So sometimes, myself included, we'll say something like z-score normalization or normalization when we're really just performing this standardization formula. So keep that in mind. Some people say normalization when you're actually performing truly standardization. So let's talk about what normalization is typically referring to. Normalization, in regards to feature scaling, is going to scale all data values to be between 0 and 1. And the way it does this is by using the minimum x value and the maximum x value. In which case, for each feature, what you're going to do is take the feature, subtract the minimum value, and then divide it by the difference between the max value and the minimum value. And that essentially scales all the data points to be between 0 and 1. So again, main differences here are standardization is fitting everything to a standard normal distribution, and normalization is scaling everything to be between 0 and 1. What's nice about normalization, it's very simple and easy to understand, although standardization is also pretty straightforward, as long as you understand a standard normal distribution. There's actually many more methods of scaling features than just typical standardization and normalization, and scikit-learn provides easy-to-use classes that perform a fit and then a transform on feature data for scaling. What we need to do is quickly discuss the fit and transform calls in more detail when it specifically comes to scaling. So a fit method call simply calculates the necessary statistics. So if you're doing things like normalization, when you call the fit method on your data, it would calculate the x minimum and the x maximum. If you're calling a fit method on something that's performing standardization, it would calculate the mean of the data and then the standard deviation of the data. The transform call is then actually scaling the data and returning the new scaled version of the data. So we previously saw a very similar process for polynomial feature conversion, where we performed a fit transform. Now there is a very important consideration we have to make in regards to when to call fit and when to call transform, and when it's okay to call both fit and transform in a single step. For the idea and purpose of feature scaling, you should only be fitting to the training data. Recall that fitting is just calculating that statistical information like the average value or mean value, standard deviation, x min or x max. That statistical information should only come from the training data. Otherwise, you're assuming prior knowledge of the test set if you were to just call fit transform on the entire data set. So if you accidentally used the entire data set upon the fit call, that would cause something known as data leakage. And data leakage means that you're getting information from the test set prior to actually training your model. And the reason for that is calculating statistics from the full data set would lead to some information from the test model or test set leaking into the training process if you were to then transform everything based off statistical information from the full data set. So that would mean if you were to call a fit on the entire data set, you could accidentally know your either min value or max value, or start to get information about the total average or total standard deviation across the entire data set. And so that's dangerous because we want the test set to be completely unseen. And doing something like feature scaling based off the entire data set, again, eventually starts to leak a little bit of information from the test set. So the feature scaling process in general would be to perform some sort of train test split and then fit only to the training feature data and then transform the training feature data and transform the test feature data. So again, only fitting to feature data from the training set and then transforming both the training feature data and the test feature data. That is your training X and test X. A very common question I get at this stage is, do we need to scale the label itself? That is the Y target label. In general, it's not necessary, nor is it advised. Normalizing the output distribution is technically altering the definition of the target, which means you're now predicting a distribution that doesn't mirror your real-world target. And this can actually negatively impact stochastic gradient descent. There's a really good post on stats.stackexchange.com, which is essentially Stack Overflow for things like data science, machine learning, and statistical learning. And I posted the link here that you can follow, which essentially has a really nice detailed explanation of why you don't need to scale the label in regards to gradient descent. So again, we only need to scale the features. We do need to scale features for both the training set and the test set, and we only fit to the training data. Now that we understand the benefits of feature scaling, let's go ahead and move on to understanding the benefits of cross-validation. I'll see you at the next lecture.